Okay, so now we will start, and I will do a first break in, say, half an hour or so, well, 15 minutes. But I will already go to the introduction so that we start the course. Again, if you have questions, please, do not hesitate. The first part will be really, really basic introduction, so it might appear trivial to you. But still, this is the basics of what we have to use, so I try to fix the framework of the course, even if it might appear trivial. So this is the first lecture, and then as I promised, I show you that. Can you see it, or is it too much light? It's okay? You more or less see it? I can improve a little bit. No, tableau. Let's see what we can do. It's a pity with this beautiful weather. Let's see. Yeah, let's do that. It's a compromise. So this is my drawing, and now we are here. So, okay, blah, blah, blah. We are here. So now we consider that we have an input which is stupid pixels. And so basically what we will do is first how to improve the quality of those images. We will first see what is an image, but that will be quick and trivial, as I said. But we will see the big methods, the big blocks, for improving the quality of your image. If you manage to improve the quality of your image at the beginning, it will make the job very much easier for the segmentation and the subsequent steps. So that's what we will do today. And next week, we will do the segmentation. So let's fix the basics. What is an image? An image is stupid pixels. So basically, an image is something that lives in a domain of dimension m, for instance here dimension 2, and that takes values in dimension n. And n might be whatever. So if I take a binary image like that, not binary, sorry, a black and grayscale image like that, each pixel has a single value, a scalar value. So in that case, my n here is 1. But as we will see later, you might have other dimensions for your image. And the domain itself can be 2 or 3D, for instance. This remains images. So basically, my image, that image here, is actually a simple function that takes value in its domain, and each pixel has a scalar value in that case. So that's basically what we have. And those points are called pixels. If we consider this image with a single scalar value per pixel, this is called monochromatic images. This is typically what you get when you do medical imaging. You get an MR or a scanner or an ultrasound image. Each pixel has a single value, a scalar value. And so that's that's the basic image that you can consider, but still a lot of applications. And when you display that, you generally display it like that. I measure a value, and I consider that that value is a grayscale value. The higher the value, the brighter the pixel. But this is just a convention, right? When I display something on the screen here, what I have to tell to the beamer is basically for each pixel, what is the amount of red, green, and blue component. That's how you create a color image. That's how you create something that you display on the screen. And so basically, when you have a monochromatic image that you want to display on the screen, you have to tell the renderer what is the color to put for each of the gray levels that you have. No, for each of the values of your pixel. It can be gray levels, so if I have a 0 value, I will put 0 in RGB, so a black color. If I have 3, it will be 3 of 255, 3, 3, so it's very dark gray, up to, if I see a value of 255, obviously I'm coding here on 8 bits, I will put a white color. But this is just a convention. I have a scalar value in my data, and I decide how to render it. And this is called a color lookup table. And I can use for the very same data another coding system for the rendering. And the same data can be displayed like that. It's exactly the same data. It's just the rendering that is different. But keep in mind that we are working with the raw data, the pixels, with their original value, the way you render doesn't matter. If you take MATLAB, for instance, and you load a picture, and you'd say, okay, a picture, a monochromatic image, with one single value per pixel, and you say, show image, so image/image parenthesis, it will choose a random color map. And then you have to tell him which color map to use. If you have color images, if you take your camera, what you get is a color image with 3 channels, red, green, blue, or any other combination of them. And so basically that means that for a given picture, you have at each voxel, each pixel, 3 components. How much red, how much green, and how much blue should I use to display this picture the more naturally? And then you can transform that to get the grayscale image. There is a transformation that you can use to get the corresponding grayscale image, black and white image, from a picture. And here we have to work with color images, so with images that take values in R3 or N3 space. But that's life. Most of the time in this course, almost always, we will work with monochromatic images because that's the simplest way for me to explain the image processing methods, because we will use some geometry and it's simpler on that. Okay? So now, let's start with the basics. For those of you who are in electrical engineering, you know that I also teach a course on signal processing. And probably if you are EE students, you had that course with me, probably, last year. And so I would like to redo a little bit of signal processing with all of you, just for the fun of it. And just to remind you the basics, some of the basics of signal processing, but applied to imaging. And this is Fourier. Yes, it's cool, Fourier. So cool. What is Fourier? Well, basically, it's a frequency analysis of a signal. I show you here the 2D Fourier transform. You know the 1D Fourier transform. You take a signal over time or over what you want, and you do the Fourier transform, which converts this signal into another representation of the same signal, but representation in the basis of Fourier, so in the basis of complex exponentials, which allows you to analyze the content of the signal in terms of frequencies, spectrum. I'm sure this is all clear for all of you. I really hope. In 2D, it's the same. If I take an image, I can do a 2D Fourier transform. Mathematically, it's simple. I have my image, and I do the decomposition in a Fourier basis, but it is a 2D Fourier basis. There are 2 axes and not 1. So you have basically horizontal and vertical frequencies. What does it mean? Well, it basically means if I look at my image, if I look at it horizontally or vertically, what is the frequency pattern that I see? If I look at that image horizontally, I will see something like a constant part here, then a sharp edge at the boundary, then a more constant part here, then another sharp edge, and then something constant. So I have something like that, right? And if you look that way, this is the signal that you will analyze by the horizontal Fourier transform along the x-axis. So basically, the x-axis will tell you what is the frequency content of horizontal transitions. And if you look vertically, you will get the content. Yes, probably some of you have to go to another course. That's why some of you are leaving, right? Who has to move? No problem. Huh? I will do a break now for you to leave, okay? Sorry for you guys. This is recorded. You will get the end of the course. And I wish you a good course after, okay? So I do a break now so that you can leave if you wish. And hopefully more will arrive. Welcome back. So just a few practical points, additional practical points before restarting the lecture. I had questions about some practicalities. For the labs, so again, you will receive on Moodle the topic of the lab, and you are free to do it when you want. Of course, if you want to get help from the teaching assistants, they will be available probably, depending on how many questions they have, but at least they will be available during the course hours, so at 8:15 till when all the questions have been asked. So basically, that's what you can get from them. If you don't need, you do what you want, of course. For the interview, though, we will try to, well, you will have to come to the interview, obviously, but we will have an extended schedule. So I will manage to have also slots outside the normal hours. So for those of you who cannot attend the interviews during the hours, I will extend it to other slots, so we'll be flexible. We'll find a way to have interviews by all of you without too much problem. Okay? What else? No, I think that's okay. I received during the course an email of one of you who cannot access the Moodle. Normally there is a key that I showed, image pattern 19. If you want to have it, just look at the slides of your colleagues to get it. And if you really cannot access, I don't know what to do, but you have to contact Moodle administration. Normally there is no restriction to accessing the Moodle of that course. You just click and you register. But maybe there is something special with one of you. But try to do that. Okay, let's go back to the course. So we are doing Fourier. So a Fourier analysis exists in 2D as well, no problem. And it has the same meaning. It gives you the frequency content. You just have to understand what is an horizontal frequency and what is a vertical frequency. If you understand that, you get an image and you can calculate its spectrum, which along two axes give you the spatial frequency content. How the signal varies through X and Y. Simple, huh? And so you can represent that by a 2D spectrum. This is the amplitude, and you have also the phase or the complex components, if you wish. And then this now allows you to see what happens when you have a digital picture. When you have a digital image, you have a sampled image. You have the real image which you have in front of you, and the computer or your eyes will sample the scene at a given number of locations. They are the pixels. So basically, when we take a picture, a digital picture, we sample that with a sampling step along X and along Y that I will call delta X and delta Y. And so basically, you know what happens when you sample an analog signal. In 1D, you remember that when you sample an analog signal, the spectrum gets replicated with a period corresponding to the sampling frequency. Clear for everybody? You remember Shannon's theorem? Sampling theory is clear for everybody? Yes? For whom is it not clear? Otherwise, you Google sampling and Shannon and you will find. Huh? So basically, you get the spectrum of your sampled image is the spectrum of your original analog image that you will never capture, but that exists, replicated along a grid. So this is the sampling grid. I sample my data along that grid, and the spectrum of that sampled data will be the spectrum of my image replicated on a grid, which is the Fourier transform of that grid. And you remember, the Fourier transform of a series of Dirac pulses is also a series of Dirac pulses. Huh? You have that in your signal processing courses. So basically, from the spectrum of my analog image that exists and that you want to sample, you get the spectrum of your image, which is the replication on the sampling, on the Fourier transform of the sampling grid of your spectrum. And this, the sampling frequency, or here the sampling pulse, omega, it's 1 over delta x, 1 over delta y. If you're in frequency, if you are in pulsation, it's 2 pi times that. Huh? So this is basically up to a 2 pi factor, the sampling frequency, 1 over the sampling step, and 1 over the sampling step here. Simple. And then you see immediately what can happen, very much like what you have in 1D. You can then, for instance, reconstruct the analog image. This is sampling theorem. If you manage to sample your image in an appropriate way, according to Shannon's theorem, then you can reconstruct your image by isolating the middle peak, very much like what you do when you do the optimal reconstruction by the correct interpolation of your analog signal from a digital signal in 1D. It's exactly the same. So from your sampled image, you can, by doing a 2D low-pass filter at the right frequency, again, refer to Shannon's theorem, reconstruct the original image, the analog image. This corresponds to doing a low-pass filtering in the frequency domain, and as you know very well, it corresponds to doing a convolution by the inverse Fourier transform of that in the spatial domain. That is theory. What does it mean in practice? It means that if you have, so that's the formula of this 2D sync interpolation kernel. Is the theory clear for everybody? Is the direct transposition in 2D of the 1D Fourier and Shannon's sampling theories? Clear for everybody? Simple, huh? What does it mean in practice? It means that you have your digital picture. And with that, you have your pixels. You can find, in theory, the exact value of the original image at any location between those pixels. So you have the value at pixel 1, 2, 3, but with that you can find the exact value with no error of the original image at coordinate 1.3 by interpolating the samples, the pixels, with this kernel. This is the beauty of Shannon theory. And you know it very well. When does it work? Well, it works when your signal, in this case your image, is band limited. And you sample it with a frequency that is at least twice the bandwidth, or the maximum frequency of your signal. This is Shannon's theory, clear for everybody, yeah? So according to the, well, as long as this assumption is satisfied, you can really find the exact, without error, value of a point in your image between the samples by interpolating with that. It's magic. Where is the problem? It's true, but under the assumption that we sampled with the right frequency, that's okay. It's true, you can really find the exact value, but what is the problem? How would you do that? By interpolating with that, right? What is the problem with that kernel? What is the problem with a sync kernel? Come on. Say it again. I see. Pardon?
It's not bounded.
Yeah. It has an infinite support. Yeah. So what I said is true. You can find the right value, but you have to interpolate from minus infinity to plus infinity in both directions, and you have to have all the samples of the scene from minus infinity to plus infinity. So it's theory, of course. In practice, what you will do is to interpolate from few neighbors, and it will give you a good value for the pixel that you want to have between the two pixels that you know. It will give you a good approximation, but not the actual real value. And you interpolate, and you decide to interpolate between 2 neighbors, 4 neighbors, and as many neighbors as you wish, depending on the speed that you want, the quality that you want, the processing power that you want, that you have. But that's the idea. Ideal interpolation, but it's just theory because it takes time, infinite amount of time and infinite amount of data. And then you can do the approximations you want to basically reconstruct the value between the pixels with a more or less accurate value. Is that clear? Why am I saying that? I'm saying that because it's important in many very simple image manipulations that you will have to do one day or another if you are handling images. The first one, of course, you will not do it yourself. The software will do it for you. But imagine you want to change the size of an image. You want to zoom in or zoom out. Well, basically, you have to know that when you do that, there is a problem of, potentially a problem of, related to the sampling, a problem of aliasing. If you increase the size of an image, there is no problem, because if you increase the size of an image, what happens is that basically you upsample, and so the only thing you have to do to upsample is really to fill the holes that when you have your image, you upsample it, so you have basically to interpolate with something that looks as close as possible to the ideal interpolation kernel. That's okay. But if you want to downsample an image, if you want to downsample it, then your frequency of sampling will change. And there is a risk that if you downsample your image, what will happen when you downsample an image? If you look at the Fourier theory, the different replicas of the spectrum that are at a distance which corresponds to the sampling frequency will get closer to each other because you decrease the sampling frequency. And so you will have the typical effect of aliasing. And so basically from an image like that, if you decrease its size without caring, if you take 1 point every second point, so if you basically throw away 1 point every second point and reconstruct the lower size image, okay, I stretched it to have the same size, but it's a lower size image, basically the replicas of the spectrum will come closer to each other. You will have basically in the spectrum of your image the appearance of replicas of the other spectra. This is the typical aliasing, right? Typical thing that you have in 1D as well. And so from that, the high frequencies of the spectrum will basically be flipped back to the low frequencies, and those stripes which are high frequencies will be flipped back in the spectrum of your image, making weird things like lower frequency stripes here. This is typical aliasing. You have to know it if you want to implement that in a, I don't know, in a GPU or in an embedded system. And the solution for that, you know it, is to do a low-pass filtering of your image before that to make sure that the highest frequency of your image after downsampling remains compatible with the frequency that you are choosing, so the sampling that you want to do now. And so you do a low-pass filtering to remove those high frequencies that will flip back and create aliasing. You remove them, and so they will not flip back. Of course, the guy will not have a shirt with stripes anymore. It will have a uniform shirt, but at least you will not have the appearance of very strange patterns there. So you really clean up the shirt before downsampling so that there is no aliasing. Is that clear? Simple, huh? So now the same happens, the same theory can be used for doing more subtle things. I told you with this system you can find the exact or almost exact, if you don't use the sync, but a very good approximation of the value of the image anywhere, even between the pixels. And this is what you can use if you want to do some geometrical transformations on your image. Take this example. You have a picture and you want to calculate the picture that is the translation of that picture by, say, 0.5 pixels. Of course, if you want to translate an image by 1 pixel, it's easy. You copy the value to the next pixel and you get your image. But if you want to create an image which is the translation of your image by 0.5, then it's a bit more complicated. And that's what I want to illustrate here. Look at that. You have your image sampled on that grid with the solid lines. So the solid line is the grid of your pixels on your screen, in your image, or in a file. You know the value of your image on the points on that grid. Now I want to calculate the translation of that image. So I want to calculate an image which corresponds to the translation of that image by, let's say, translation in that direction. So basically, this point will move here, okay? A non-integer number. So basically what I know is that in my final image, this point will correspond to a point here, which is between the pixels. But what I want is to find the value of the pixels of that resulting image such that the result is a translated image. If I show you the picture on my computer, doing a translation doesn't mean that I move the screen. I keep the screen at the same place, the grid remains the same, and I want to replace the pixels, but the new pixels such that it looks like my image has been translated. So basically, I want to know what is the value that I have to put here, such that the image is translated, and what I know is that actually I know the values there. And I want to find what is the value there. And so obviously what I have to do is to say, okay, to find the value here, I will interpolate by a sink or any simpler approximation you choose, depending on the quality of this operation you want to do. But if I want to choose what is the value here, I will interpolate between the values that I know. And so basically I know that value because it comes from there. I know that value because it comes from, I don't know where. That one will come from, where is it? That one will come from here. Where am I? That one is that one. And that one is that one. So basically, if I want to find the value here, I know that actually it corresponds by the reverse translation to a point here. And I know those 4 points. And I know all of them, actually. So now what I just have to know to put the correct value here is interpolate by among the neighbors that I know. So interpolate among the neighbors that I know. Find the value of that point, knowing all the others in white. And so basically it's a simple question of reconstruction of the true value of the image between the non-pixel. This is exactly what I explained before. So you basically say, okay, this is coordinate, I don't know what, 1.2 and 2. I don't know what. And you say, okay, fine, I will interpolate among the neighbors. How many neighbors? You choose. You want to do a very good estimation of the translated image, you take a lot of neighbors, ideally an infinity, otherwise a lot of them, and you interpolate by something that looks like the interpolation kernel, the sink. and then you get the value here, and you place it there, and you do that for everyone. So basically the key idea is when you have to do an operation like that, which will basically change the positions of the pixels, you will basically have to say, what are the values on the grid of my final image? And to find the value, you use the inverse transformation, find where it is, and interpolate the way you want. This is valid for translation, but this is actually valid for any geometrical transformation. For translation, is it clear? Do you want me to repeat something? So if you are doing medical imaging, or you're doing satellite imaging, you will have to do this kind of translation of one image to match another. You will have to find how to superpose 2 images, say, of the same patient at different time points, or with 2 different modalities, or satellites coming every day. You want to superpose the images, so you will have basically to find the right translation of one image with a sub-pixel accuracy. You might want to implement that yourself, and you have the choice of doing that with the accuracy that you want, interpolating among the 4 neighbors or more, depending on the accuracy that you want, the constraints that you have in terms of real-time processing, and so on. The only thing you have to remember is that the more points you take for interpolating, the better it will be. And it's always taking the coordinates of the point you want to find in your final image, do the inverse geometrical transformation, find the coordinates in the original of the point that you want, and find its value by the interpolation you choose depending on your constraints. And that is actually what you do also in the very advanced software. If you use Photoshop, you have the choice of the interpolator when you do translation rotations. You don't know, but it's hidden in the parameters. You can decide to do very advanced and pretty slow interpolation or very fast. If you implement that on a camera, on a chip in a camera, you will have to decide, depending on the processing power that you have in your embedded system, which interpolator you use, because it might be too much for the power of your system. So you have to know that. That's why I'm saying it. And it's actually valid also for other transformations, the rotation. You want to take an image and superpose it to another, so you want to rotate it. How do you calculate the rotation? You know the pixels of your image, and you know that that pixels will go there, that pixel will go there, so you know also the points in the dashed line here. But you don't want to turn your screen. You want to reconstruct a straight image that corresponds to a rotated content. So basically, you know those points here, but what you want to know is the point here. So you basically have to find the value to put here by interpolating between the neighbors. So basically you say, okay, this point comes from there. These points will therefore come from there by inverse rotation. If you want to calculate an image that is rotated by theta, you take the coordinates of each of the pixels of your final image, you rotate those coordinates by minus theta, it gives you a non-integer coordinate here, and you interpolate by 4, by whatever, by 9, by what you want, depending on how precise you want to be. Okay? And you get your rotated image. There is a very good test that you can do. Take your preferred software and take a picture and then do 36 rotations of 10 degrees. So rotate it by 10 degrees. Then the result you rotate it by 10 degrees. Then the result you rotate it by 10 degrees. And you do that 36 times. So after that you should get a straight image again. And you will see how degraded the image is. Because each time you do a rotation, you will have to do this operation and interpolate the value here among the neighbors. And depending on the interpolation that your system will do, each time you lose a little bit of information. You would not lose information if the system would do an interpolation with all the pixels from -infinity to infinity. But that is never the case. It does some kind of interpolation about the closest neighbors, the nearest neighbors. And so basically each time you do that, the value that you put here is actually not the real value, the actual value of the original scene. It's an approximation. And if you do that a certain number of times, each time you lose information. And so after 36 rotations, you will see that your image is really blurred because the value that you get at the pixels has been degraded a lot of times. You can try that once if you wish. What is funny is that you can do the same with other transformations. So at the end, what you have is basically, each time you have to say, okay, I want to do a rotation by an angle theta. And so what you do is the inverse. So you basically search for each coordinate of your final image, xy, what is by the inverse rotation the coordinate in the original image. So you want to find point 1, 1 here, you put 1, 1 here, you calculate, this gives you a non-integer coordinate, and you interpolate around that to find the value there. And this is more general than just translation and rotations. You can do any kind, for instance, of linear transformation, where you basically say, okay, I do a transformation which is parameterized by a certain number of parameters from the coordinates in my final image to the coordinates in my original image. So I take the coordinates of my final image for a given set of parameters there. It gives me the coordinates in the original image, non-integer. I find the value that I have to put there by interpolating, and I put it in xy. And depending on the parameters that you put there, you can create a translation. If you put thetas, sinus and cosinus theta there, you will do a rotation. You can do a zoom by putting scaling factors here. But you can even do nonlinear transformations. You can say, okay, I implement a geometrical transformation by calculating the coordinates in my original image, depending on the coordinates xy in my final image, by a complex formula. And this will implement some kind of strange deformation of your image, but that's funny. So you fix the values of A1, A2, and B1, B2, etc. And this, by calculating the geometrical transformation from the original to the final, by those parameters, will implement some kind of funny deformations like that, for instance. And it allows you to calculate a very nice, precise image where you have values at each point corresponding to a geometrical transformation that you can parameterize. And by changing the parameters here, you can deform differently. Why is it useful? Well, you might want to take an image and actually find the right deformation of it to match another image. This is, for instance, the case in medical imaging. You take two images of two different people. This is one patient, this is another, in two different modalities. No, this is not true. This is the same patient in two different modalities, MRI and PET scan. And here you want to find the registration by calculating the translation and the rotation. So basically, you want to find the translation vector and the rotation angles that you have to apply to one of them to superimpose to the other. And so basically, you have to implement what I explained for translation and rotation, and then iterate to find the right theta and the right t vector. But those more complicated, sophisticated deformations can be applied when you have a given image of a given patient and you want to match it to another patient. Then you might want to deform one of the images. So you might want to say, okay, now what I'm trying to find, I implement this, and I try to find the parameters of the transformation such that the two images come closer to each other. So those geometrical transformations, they have very practical applications. This linear transformation here would allow you to rotate, translate, but also, depending on the parameter, do a shearing, so a deformation, of an image to match it. This is typically what you would do in satellite imaging, when you take one image from the vertical incidence and another one from a non-vertical incidence. So you have a perspective problem. And you have to basically rotate, translate, and also distort one of the images to match the other. And this is typically what you will do by finding the right parameters in that kind of geometrical transformation. Remember, you always start from the final images, you find your transformation, you do the inverse transformation, it gives you the coordinates in the original image, you interpolate and you put it back in the final image. And if you want to find the right transformation, your problem is to optimize those parameters. But it's always the inverse transformation. And that's very important. Is that clear? Do you want me to repeat something? You all understand why we have the inverse transformation and not the direct transformation. Okay? I assume there is no question, so I assume you understand. Huh? If it's not the case, please do ask. Okay, I'm moving on. Now I will change the topic. This was for the geometrical transformation. Now I want to see another block. Nothing to do with that, but still in the pre-processing. So we are still trying to improve the images from the beginning. And here I will show you what is histogram equalization. This is a very famous pre-processing that you might want to do on natural images or computed images. What is the problem that we want to tackle? If you acquire an image, either a natural image or an image computed, like this computed tomography, this is a slice of a lung, and you see, or you don't see actually, there is the heart somewhere, these are the lungs, and you have arteries in the middle. And this is the image that you get from your CT scan, your scanner. And if you look at the histogram of that image, do you all know what an histogram is? This is the count of how many pixels I have for each possible gray level. If you looked at the histogram of that image, you see that there are two regions, one quite dark and one quite bright. You have many pixels that are quite bright, many pixels that are quite bright, many pixels that are quite dark. Of course, those pixels are all those pixels of the lung, and those pixels are all those pixels of the tissues. But if you look carefully, you see that there are actually two peaks here. In the black pixels, you have a large number of very black pixels, very dark pixels, and also quite a large number of just a little bit brighter. You don't see them. The contrast is so close to each other that you don't see them. But they are there. And the same applies for the bright. You have a lot of bright pixels and a good number of even brighter pixels, probably the bone here, while those ones are probably the tissue here. But they are so close in contrast that you almost do not see them. What we would like to have is to have a histogram that is better shaped. It's a pity we have a range of values here that are almost not used. There are in that image no really black pixels. It's a pity. And all the contrast is concentrated in few bits. It's a pity, because they are so close to each other that you don't see them. What you ideally would like to do is to have an histogram that is more spread over the range of values. You would like, ideally, this peak to be here, to leave enough contrast between that region and that region. You would like to take this peak and transform the values to put them in an area where you have no values, so that those tissues become more different than those ones and you see them better. And this is exactly what histogram equalization will do for you. It will change the values of the pixels such that the histogram is more equilibrated. Ideally, in an ideal continuous space, the histogram should be completely stretched and become flat over the whole range. You really want to distribute the content over the whole range to increase the contrast between regions. So what histogram equalization will do is try to find what new value I have to put to each pixel with a given value. We will change the value of that pixel such that with the objective of having a histogram that is much more conditioned. So if you put that in mathematical terms, what we want is to find for a given value of the pixels from 0 to 255, for instance, what is the new value that we have to put to those pixels? What is the new value of, imagine that this is value 100, and this is 110, let's say. What is the new value of all the pixels that have a value 100, such that the histogram become more flat? Well, the pixels that have 100 should become pixels of maybe 10, I don't know, we'll see. So this is the transform I'm trying to find. What is the new value that I have to put to all the pixels that have a value p, with the objective of generating a histogram which is more spread and more flat over the whole range. No peak like that, but more distributed, and ideally equally distributed. Now, to do that, we will do just a few equations. We are working in a discrete environment. We have pixels of discrete values, 0, 1, 2, 3, up to 255, let's say. This is the histogram of the final image, and this is the histogram of the original image. H is the histogram of the original image, G is the histogram of the final image. What I'm writing here is the sum of G is equal to the sum of H. Why can I write that? The sum of the values of the histogram after my transformation is equal to the sum of the values of the histogram before my transformation. Why can I write that? What is... Pardon me?
Number of pixels to maintain.
Yep. What is this sum? This sum is what?
Basically the sum of the whole pixels and the normalized.
Is the number of pixels. The sum of the values of an histogram, each value of the histogram is the number of pixels of a given value. If I sum that for all the values, I just get the number of pixels in my image. That's what you say. So this sum is the number of pixels in my image. And I don't change it. My result will be an image of the same size. So basically, this equality holds because this equals this, because both of them are the number of pixels in my image. And my objective is to have the histogram of the output image as flat as possible. In an ideal continuous world, it should be the number of pixels, n square is the number of pixels. It's not the square of the number of pixels. It's the number of pixels, assuming that n is the dimension of my image if I assume a square image. I could write n if you wish. But my histogram, in an ideal world, should be flat. And since it should be the number of pixels, the value of that flat histogram, the height of that flat histogram, is the number of pixels divided by the range of my image, from 0 to 255. So it's the number of pixels divided by 256 in an 8-bit representation. Huh? That's the goal. I want to find a transformation that approaches, that implements an output image with that kind of histogram. And you will see why I'm insisting on the fact that this will be true only in a continuous setting. But let's do it. So from my initial histogram, I want to find a histogram that as much as possible is completely spread, and I distribute the values over the different bins in an optimal way, such that in an ideal world it should be like that. Now I take this and I rewrite it. If G is this, then the integral from the first to the last value, from 0 to 255, for instance, of my histogram is the number of points. I calculate it, and it's also the integral of the other, because of this equation. Huh? And again, here I'm mixing a little bit the discrete and the continuous formulation. This is a kind of a simplified way to explain it. It's not extremely rigorous. But the total number remains the same. That I can easily calculate as an integral. It's easy to calculate. So again, Q0 and Q0 and Qk are the range of my output image. Let's say it's 0 to 255. So if I integrate from 0 to a given value of that, it corresponds to the integral from 0 to another given value in the original image of the original histogram. I'm solving now this. So basically I get this. So for each value of my integral here is the same here. I can isolate now what is Q, which is Q is this. And so now I get Q equal that, if I play with that. And this tells me what is the transformation. If you get in your original image a pixel of value P, say 100, what you have to do, according to this formulation here, is to integrate the histogram of your image from 0 to P, to 100. You accumulate the number of pixels, you normalize that, and this is the value that you have to give to all the pixels that had a value P in your original image. If you give them a value Q, it will ultimately create a histogram that is as flat as you can. So basically, it's really an accumulation. You start from 0, you integrate from 0 to 0, that's easy. But then you take P equal 1, and you accumulate, you integrate your histogram from 0 to 1, you normalize, and this is what you will get here. Then from 0 to 2, and you basically accumulate and pull towards you the different bins such that they become spread. And that's exactly what this integral does. The discrete formula is this one. So basically, to calculate the new value of your histogram, of your image, you take the sum between 0 and the value that you want to transform of your histogram, you normalize it a little bit, and you get that. And what you get at the end is this. This is your original image with its original histogram. After really pulling the different bins towards 0 and accumulating them until they reach the value that you want to reach, which would be the value of the flat histogram, you pull them down, and basically from that image you get that image, and from that histogram you get that histogram. You really see what it does. It really puts together all those bins here in one bin to get the first bin here, and then it keeps accumulating as much as it can in a discrete manner. So sometimes it's not possible to reach n square divided by q as we had. But still, it pulls and fuses the bins such that overall, with the problem of the discrete histogram, it looks like a kind of a flat histogram. At least much more equilibrated, and now you see the tissue appearing. What you see appearing in gray here is what you had there that you were not seeing. But now you see them because they are more contrasted with respect to the background, which is now here. And now you see much better the content of this area where you had actually, indeed, two tissues, but now they are better visible. Let me again repeat why this is not really a flat histogram. We have discrete bins. Some of the bins have low values, some of the bins have high values. What this histogram equalization does is redistribute the content of those bins with the objective of generating a flat histogram. So it will take the first one, put it in 0. The second one, put it in 0. The third one, put it in 0, until you reach the value that would be the value of a flat histogram. And then it stops. Then it goes to the next one. It keeps pulling. But of course, at some point, there are bins that are higher than that one. And you cannot split the bin. It's a given pixel value. So you basically pull it down, and that's it. And too late. It's already beyond the value that you're targeting. So you stop. And you keep doing that. And you see that the big bins, they are actually really split. The small bins, they are agglomerated. They are putting together to one single value. That's how it works in a discrete world. So this is the best you can do to make your histogram as flat as possible. The result being an image that is much more readable. Okay? You have to think about that. It's not obvious to understand why you don't really have a flat histogram. But if you think twice, you will see how it works. Questions, comments? Okay for you? Very good. Let me move one step further, and then I will do a last break. Yes. We are now opening the last part of this lecture of today, which is about denoising and image enhancement. I will not talk too much about denoising. Denoising is an extremely vast topic. It aims at removing noise in images. You might have noise from many different causes, reasons. It might be electronic, it might be external noise, it might be amount of light that you get on your sensor, the quality of your electronics, whatever. But you have noise in images, which is by nature a random signal. And so the classical model for the image that you have is to say, the image that I have is actually an ideal image plus noise. This is a model. This is how you model the fact that you have noise which is added to your image. And this is true for the systems that indeed add noise to your image with a plus. That is called additive noise. But in some acquisition systems, the noise is proportional to the pixels, so it's not additive, it might be multiplicative. But in many situations, it's a good idea to model the image that you get as the ideal plus noise. It corresponds nicely to the reality. And you can measure the amount of noise by the so-called signal-to-noise ratio. Now the question is, how do we remove noise? Well, noise is added. Noise is a random signal that is added on your image. If you have a random signal, you can estimate its statistical properties. You know about random signal, you cannot write the equation of a random signal, otherwise it's not random. But you can estimate the statistical parameters of this random signal. You can estimate its mean, you can estimate its covariance and things like that. And so let's imagine that the noise that is added on your image is a zero mean noise. Sometimes the ideal value is increased by a certain random noise, and sometimes it's decreased. So the noise itself has random values, but the mean of this random signal is, let's say, 0, which is realistic in many situations. So let's say that we have a zero mean noise. Then what is the simplest way to remove that noise? Well, the simplest is, I take the picture, it is affected by a zero mean noise. If I have the opportunity, let's take another picture, and another, and another, and another. Take 1,000 of those pictures, calculate the average. The average of the image could be the image. The average of the noise will tend to 0. Of course, you don't have the flexibility with your iPhone or your telephone to take 1,000 pictures and take the mean. But this is possible in some situations. And just to give you an example, when you do an MRI, a magnetic resonance imaging of your brain in a hospital, they take 5, 10, a certain number of images, and they average them. Because that's the way, that's a very good way, and if they have the possibility to do it, it's better, to reduce the noise in the data without affecting the data themselves. So it looks trivial to say that if you have many images, you calculate the estimate of that so by the mean, and you get a good estimate of your image, reducing the noise. Most of the time you cannot do that. But it exists, more than you think. But the most classical way to reduce noise in images is to do filtering. You have your image, and you pass a filter on it. And, as you certainly know, what we typically consider to reduce the noise is a low-pass filter. Why? Why do you think that applying a low-pass filter will reduce the noise in an image? Any idea? I'm sure you know. Yeah.
Noise is generally zero, which means that I've got like very low, almost zero frequency signals, but very high frequency.
Okay. The fact that it has zero mean has nothing to do with that, but generally we say that the noise indeed has a high frequency content. This is generally termed as white noise, right? A white noise is a noise that has a spectrum which is like the white light, flat over a wide range of values. So the noise has a very large frequency content. What we call white noise is really a frequency content that is uniform on a range. It can be something else than white, but generally the noise has a large frequency content. While the images themselves do not necessarily have the same frequency content. Most of the time, the natural images themselves, they have a more low-pass characteristics. There are a few edges, but most of the time, the content of an image is in the low frequencies. So doing a low-pass filtering, which means removing the high frequencies, will remove everything at high frequencies, but statistically, in average, you will remove more the noise than the image, because you will have more noise in the high frequency than image content in the high frequencies. So, the wrong answer would be, the noise is high frequency. No, the noise generally has a whole spectrum of frequencies. But the content, the energy of the noise in the high frequency is very often higher than the content of the image. That's why we do a low-pass filtering, because it removes the high frequencies of the whole image, including the image and the noise, but statistically, or in average, you will remove a lot of noise and you remove a little bit of the image. And this is what you see here. How do you do a low-pass filtering? Well, basically you can calculate by convolving your image with a mask, convolving, to do the 2D convolution, a mask of a low-pass filter, being an average filter or something more sophisticated, but basically you average the neighbors. This is a low-pass filter. Yeah? And what it does is this. Consider this image and its noisy version. In that image, as I showed you before, this is the same image as before, the spectrum was a little bit like that. And remember, it was a peak. So there is high energy at the low frequencies and a little bit of energy in the high frequencies. The noise has a spectrum which is much more white, uniform. So basically, if I low pass that, I will remove a lot of energy of the noise, unfortunately also a little bit, but not that much of the image. And this is what you see here. If I filter, I remove a lot of the noise, but the more I filter, the more I remove from the image as well. That's life. And you see that the image becomes blurred, because you also remove the high frequencies of the image, not only of the noise. You remove a big share of the noise, indeed, but you also remove the high frequencies of the image. This is the drawback of doing a linear low-pass filter like that. But that's life. Okay? Yes? Well, basically, you have the answer here. A 3x3 or a 5x5 pixel filter will basically filter with a different impulse response. This is the impulse response of your signal. And if you calculate the Fourier transform of that 3x3 and the Fourier transform of the 5x5, what will happen is that you filter less by that than by a 5x5. A 5x5 pixel signal will have a smaller bandwidth because of the Fourier transform of a rectangle. So basically, the bigger the filter, the more you smooth, because you calculate the average on more points. And the Fourier transform of that will be actually will filter less than the Fourier transform of a bigger filter. Okay? Other questions? So, simple low-pass filtering. Still, it's used a lot. Huh? But we can do better. One word about the case when the noise is not additive, not multiplicative. There are tricks. I let you read that by yourself. Now, what I explained before is the linear filtering. Linear filtering, you convolve your image by a low-pass filter. You get a reduction of the noise, but you also get a degradation of your image. And I would like to show you a few non-linear techniques that do actually better. Some of them I will let you read them in the slides. One of them I will focus on. So, linear, you basically take a filter, you convolve your image with that filter, you get a result. Drawback of that, you cannot really select whether you degrade the image or the noise. You do what you can. Advantage of that, what is the advantage of doing a linear filtering, a convolution? What could be an advantage of filtering an image with a linear operator, so with a convolution? You know how we do a convolution very quickly? How do you do a very fast convolution? Oh, come on, yeah. Yes, you do a fast Fourier transform. Huh? So, doing a linear filtering means doing a convolution, and you can do extremely quickly by a fast Fourier transform. So that's the advantage. It's very simple. Drawback, well, it does a linear, so it doesn't select whether you remove noise or data. In the non-linear versions, you don't have the advantage of very fast implementation, but you can do more sophisticated stuff. I will let you read what I have in those slides. I will just focus here on one of them, which I like very much. I focused on one that I like very much. I focused on one that I like very much. Do you see what I mean? Okay? Keep in mind that we will have an interview one day. Keep that in mind. It might be overrepresented in the papers that you will have to choose when you do your exam. I like it very much. Get the message? Okay. What is it? It's called the median filter. The median filter is not a mean filter. A mean filter is the one that I have seen before. You replace a pixel by the mean of its neighbors. It's the linear low-pass filter, the simplest linear low-pass filter. A median filter is a filter where you replace the value of a pixel by the median of its neighbors. And what is the median of a group of pixels? I will explain now. The median is actually, when you take a group of values, the median value is the one that you obtain when you sort the values in increasing order, and you take the one in the middle of the list. You probably have already seen your median mark, or the median opinion is the opinion for which you have the same number of people with a higher score or a lower score. Okay? So the median value is not the mean value, it's the median. You take them, you sort them, and you take the one in the middle of the list. Clear? And that's what we do here. Let's take this 1D example. It's a simple 1D line of an image, binary, 0, 1. It's a very simple example, but generalizing to 2D is trivial. I have this pixel, those pixels here, along a line, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. I want to do a median filter of that, of size 3 in 1D, 3 by 3 in 2D, for example. That means that I will take the pixel and look at its neighbors. In my 1D case, the two neighbors next to each other. I take them, so if I take this pixel, for instance, the neighbors are those two, 0, 1, 0. I take the three of them, 0, 1, 0. I order them, 0, 0, 1. Median value, 0. So filtering that part of the signal by a median filter of size 3 puts that pixel back to 0. I keep doing that for that pixel. 1, 0, 0, 1, 0, 0, 0, 0, 1, 0. You see what I mean? You get 0. I keep doing it, 0, 0, 0. Here, you have 0. 0, 0, 1. Median filter, 0. Here, 0, 1, 1. Median 1. 0, 1, 1, median 1. Here, 1, 0, 1. 1, 0, 1. 0, 1, 1, 1. So this one gets back there. And so after that, you get that. What do you see? You see that what it does is that it replaces the pixel by somehow what is most represented in its neighborhood. So if you are here, obviously you are leaving an area of value 0 with a little exception there, and entering an area of values 1 with a little exception there. This exception is really an exception because its neighbors are 1. This is really an exception because its neighbors are 0. But the rest is really clearly zeros and becoming 1. And after the median filtering, you really get that. So it removes really what is really like an exception in the middle. But when you have a steady transition from one region to the other, it is kept. And that is the beauty of the median filter. It's extremely simple to implement. You sort the neighbors and you replace by the median value. But it allows you to keep very nicely the contours. Because when you have a contour, you really move from a region of, say, low value to a region of high value with little exceptions. This strong transition is kept. but the little exceptions are destroyed. And you really see it in an image, and it is really amazing. If I take that image, extremely noisy image, with a lot of little points, which are obviously, each of them are obviously an exception considering their neighborhood. Replacing each pixel by the median of its neighbors gives you that image. So you see how powerful this median filter is to remove what is called salt and pepper noise that you can get when you have an electronic noise, for instance. This is really the result of that. There is no smoothing of the edges. The edges remain sharp because they are strong transition between a region and another. They are not exceptions. And it also works a little bit less, but it also works quite nicely when you have noise that is more coherent because the pixels here are less an exception. But for strong noise like pepper, white salt and pepper noise, this is just amazing. Okay? I suggest that we do a short break and then we finish. I have for another, what? Half an hour and then I will be done. So we do a short break of 10 minutes and then we'll finish, and we'll finish earlier than 12. Okay for you? 10 minutes break. Thank you. Okay, welcome back. Take your seats. So let's move on and finish. So now we have seen a little bit in a few minutes what are the main methods to do denoising. I will not see more. There is vast literature on denoising. I will not see more in this course. I want to finish with something which is the opposite, and then I will be done. The opposite is this one. We will do the opposite. I want to do something now which is, I have an image, and for any reason, this image has been blurred. It's kind of blurred. Typical example, you take a picture, and if, like me, you are not a very good photographer, there was motion and you didn't tune your parameters, so you have blurred by motion. Or the focus was not totally correct. Or the lens is distorted, which happens very much, for instance, in telescopes. Or whatever. You have an image and it is low pass. So what is called, well, the first thing is called contour enhancement. Those contours has been blurred and you want to enhance them. So the very natural way to do that would be to apply a high-pass filter on your image, which is obvious. The image has been degraded by a low-pass filter. By applying a high-pass filter, you will boost the high frequencies, so you should recover most of the contours, the high frequencies. High-pass filter is something like that, which corresponds mostly to the difference between the pixels, not the mean, but the difference. In different variations, you can calculate their frequency response of those impulse responses, and they really look like high-pass filters. Okay, what does it give? Well, it works. From that image, if you high-pass filter it, you get that image. Much sharper edges. And from that old radiograph, you get a much sharper radiograph. Look at the contours here. They are much better visible. Look at the bones there. They are more visible here. They were there, but very blurred. You see them a little bit better in this very old restored radiograph. Same for this angiograph. Original and much better. Obviously, the edges are sharper. If you want to detect the vessels, it will be easier here. So this is fine. But at the end of the day, what you have is putting a high-pass filter on an image. What is the danger? Obviously. Of course. If your image has noise, you will boost the noise. So that is a trivial solution when you have a very clean image. But now, let's see what we can do. This is called image restoration. When you have this blur with noise. And this will be the final series of methods that I will see in this presentation. And I will be done in a few minutes. This is called restoration. We want to invert something that happened to my image which is not wanted. I am a bad photographer. I took a picture which is blurred, and obviously it's noisy. I'm really bad. I want to invert that. I want to do, and you will understand quickly why, I want to do what is called deconvolution. And you will quickly see why. For this last part of the lecture, I will introduce a little bit of formalism, and so just follow me there. You will understand my notations. I want to find the ideal image. The ideal image is the one that I would have taken if I would have been a fantastic photographer. Ideal, sub-I. Unfortunately, I'm a bad photographer, so I got an observed image. It's the one I got. And of course, my goal as an image processing person would be to take that observed image and try to estimate as much as possible what has been the ideal image behind that. So I have that, I want to get that. And I will write the model of that. From the ideal image, how did I manage to be so bad? Well, I managed to be so bad because my image that I get is actually the ideal low-pass filtered, convolved. Double star means convolution in 2D, but it doesn't matter. Convolved by a low-pass filter. My blur is a low-pass filter, obviously. And on top of that, I'm really bad, I have noise. So this is the model, the basic model of what I observe. And this is basically what we want to invert. I have that. Can I estimate that? Can I deconvolve FO to get something that looks like FI? Deconvolve, undo the convolution, knowing that there is noise. So keep in mind this model because that's the basic model. Assumptions there, quite a lot. We assume that the unwanted effect is a linear low-pass filtering, which is quite reasonable when you have blur because of the camera, when you have focusing blur, when you have motion blur. We'll come back to that. And you have noise, and we assume that it is an additive noise, as you can see, because of the plus here. Those assumptions being taken into account, this is the model of the picture that I'm acquiring as a bad photographer. Now, let's try to restore that. Let's try to see. Let's imagine now that we also know, we know how bad I am, how bad my camera is. We managed to find a way, and I will come back to that on how to do that. We managed to find a way to know what is the low-pass filter, how much we blurred our image. This can be estimated by calibration. I will come back to that later. So we kind of know the quality of our system. Still, it does the convolution. But let's say we know what is HD, and we know, of course, we know the image. And let's assume also that we can have a good estimate of the statistical properties of the noise. Under those assumptions, what can we do to have an estimate of Fi? So let's do it. Okay. What I want is now to find a filter HR for restoration, the filter that will undo the convolution. I want to find the filter such that if I convolve that filter, that my observed image by that filter, it will give me something which is close to Fi, to my ideal image. So the question is, what is the best filter to apply such that when I convolve it with my observed image, it really undoes, it really undoes, I don't know if I can say that, it does the job of removing the convolution. Let's write it down. Remember what is the model of FO? The model of FO is that. Right? So my estimated image is my observed image convolved by the restoration filter that I want to find. If you prefer writing it in the Fourier domain, the Fourier transform of my restored image should be close to the ideal. My restored image is the product, well, is that, which is the Fourier transform, convolution becomes a product, of my observed image multiplied by the Fourier transform of my restoration filter. And now comes the first solution, which is not necessarily good. But intuitively, if you think naively, think naive. what would be a good idea for the restoration filter as a very simple first approximation?
1 over HD.
Yes, 1 over HD. Because obviously, it will undo that. And this is what you can do. This is basically what I did just in the slides before. You can do what is called the inverse filter. And it is called inverse filter. I might ask you that also when we will meet one day or another. It's called inverse filter because the Fourier transform of the restoration filter is the inverse of the Fourier transform of the degradation filter. If you tell me it's called inverse filter because the filter is the inverse, it doesn't mean anything. The filter is not the inverse. The Fourier transform of the impulse response of the filter is the inverse of the Fourier transform of the impulse response of the degradation filter. Or the frequency response of the degradation filter is the inverse of the frequency response of the restoration filter, and vice versa. So let's be precise. It's called inverse filters because in the Fourier domain, they have one is the inverse of the other. And you might already imagine that it might not be that trivial to build it because there might be instabilities, because dividing by 0, but that's another story. But so, if we assume that our system is calibrated enough so that we know how bad it is, we know HD, so we know its frequency response, we know how low pass it is, then you can build a restoration filter up to the stabilities problem that I don't describe here. You can do the high pass filter that will compensate that. And it's beautiful because your restored image in the Fourier domain will really be the ideal image plus a high pass version of the noise. And again, if the noise is negligible, if you have little noise in your image, you will get something really, really nice. It will really restore your image. Your image will be really the ideal image plus some high pass filter noise, but if your noise level is extremely high, that might be a very good solution. Very simple and good solution. But of course, if you get a little bit more noise, this will be improved. This will be increased, boosted. And that's where we have to do something more than the inverse filter. But for some cases, the one I showed before, the old radiographs, for instance, it was probably good enough. And it does the job. But, okay, this is a graphical representation of the same. If your ideal image has that kind of spectrum, I will show you those kinds of graphs in the next slides. They are just 1D representation of what should be a 2D spectrum. But the 2D spectrum is not that easy to draw and to visualize. So it's a kind of, say, one line of the 2D spectrum. Huh? But it gives you the message. If your image has that kind of frequency content, and it has been blurred by a low-pass filter, obviously what you have to use is the inverse of the low-pass filter. It's a high-pass filter. And it will indeed boost the high frequencies. If you have noise on top of that, it will boost the high frequencies more than the low frequencies, and it will boost the noise. But if you have no noise, it will really undo the low-pass filter. So if by the low-pass filtering, your content at some frequencies has been decreased, that's really what a low-pass filter does. It decreases the frequency content at the high frequencies. Well, basically, your filter will be 1 over that. So when you will multiply that by that, you will get 1, and you have your restored image. Of course, it becomes unstable if the degradation filters has zeros in its frequency response, because 1 over 0 will be unstable. But except that numerical problem, the concept is really holds. Is that clear? Simple, huh? Now let's move to what it gives. For the moment, what I've done is simple. I don't think you can see anything there. I'll try to switch off the light, but not sure it will work. No, that's not what I want. It should. Gradin, yeah, and scène. Yeah, let's say. Let's imagine that you see something. An original image, the contrast is really bad, I know. Blurred image, blurred and noisy image. Now, if I restore it, this is what I have. If this is the restoration of just the blurred image. Let me tell you what you should see, okay? Original image, nicely sharp. Blurred image, not so sharp. Blurred and noisy, obviously you see the noise. If I restore that image without the noise, I get again a very sharp image. It really works. If I restore the image with the inverse filter of the noisy image, I get a lot of noise. That's what you should see in those pictures. If you don't see, trust me. Now let's see the last contribution of this lecture, which is what you have to do if you have noise as well. Let's try to make it intuitive first. The inverse filter is the best solution when you have no noise. It remains a good solution, rather good solution, if for a given frequency you have more power in your image than in the noise. Because of course it will boost that frequency, but you will restore significantly your image, while if the noise is small, increasing a little bit the noise. But on the contrary, the inverse filter will be a bad idea if you do the inverse filter at a given frequency, if the power of the noise is much more than the power of the image. Then what you will have is basically an amplification of the noise and a marginal restoration. Or a good restoration, but hidden in a huge noise. You see that? So, what is the ideal solution now? It's called the Wiener filter, which is a filter, to see it intuitively, is just a filter that at each frequency will estimate whether it is worth or not doing the inverse filter. Is it worth doing the inverse filter? By estimating the amount of energy in the image and the amount of energy in the noise at that frequency, and decide whether it should really boost that frequency or not, depending on whether you have a lot of image and little noise, or a lot of noise and little image. And at each frequency, the Wiener filter will basically estimate the amount of energy in the image, the amount of energy in the noise, and decide, based on the ratio between the two, whether it's a good idea to boost that frequency by something that should be an inverse filter at that frequency, so a value which is the inverse of the degradation filter in frequency domain, or not. Do you see the intuition? Do you want me to repeat? This is very important, this intuition. Because the math will be extremely simple if you get the intuition. Is the intuition clear? Do you want me to repeat? Who wants me to repeat? Say it then. Come on. You understand the inverse filter? If I have no noise, the inverse filter is, in the frequency domain, an amplification which is the inverse of the attenuation that was generated by the degradation filter. In the frequency domain, the inverse filter takes the different frequency and multiplies them by a value which is the inverse of the degradation, such that it really reverses the effect of the degradation for each frequency. For each frequency, the restoration is the inverse of the degradation. And since I'm convolving my image by that filter, in the Fourier domain, I'm multiplying by that. And if I'm multiplying by that the spectrum of my observed image, this will undo the effect of the degradation filter. And I get that. Plus noise. That's okay? So it's a good idea if I have no noise. And if I have a lot of noise at given frequencies, this noise will basically be boosted by the inverse filter. Is that clear? So now, obviously then, an adaptive filter would basically have to estimate for each frequency whether this term is big or not. If the noise is big as compared to the content of the image at that frequency, at a given frequency, you should certainly not do the inverse filter. But if at a given frequency the content, the power of the image is much bigger than the content of the noise, then it's certainly a good idea to boost this frequency back to its original value, because you will basically restore your image, and since at that frequency you have little noise, okay, it's acceptable. That's the intuition. Is it more clear now? So now let's see how we implement that. There is a mathematical way to implement that, but the interpretation at the end, you will see, is exactly what I said. We want to find the restoration filter, and I will go quickly on the math, you will do that yourself. The restoration filter is what I want, is my unknown. And I want to find it, and this is the trick, such that it brings my restored image very close to my ideal image in a statistical sense. Since they are random signals. Huh? I want to minimize this difference. You will tell me, yes, but you don't know Fi. Sure. But I can have a statistical estimate of the parameters of Fi. You will see. So I want to find HR such that this is minimum. Where is HR in this? HR is here. Because HR is hidden there. This is FO convolved by HR. Yes? And FO is Fi convolved by HD plus noise. You follow me? So basically, I want to minimize this with respect to HR. So simply, in a simplistic view, I just have to derive this with respect to HR, equal it to 0, and solve this equation to find what is HR. So let's write it. HR is hidden inside here. Let's derive that by HR. It will be 2 times this times the derivation. And if you remember that Fi hat is Fo convolved by HR, then you have 2 times this times the derivative of this, which is actually Fo convolved by HR, is just HR, just Fo. So the derivative is 2 times, which I suppress, that times the derivative of that, which is actually Fo, because this is Fo convolved by HR. The derivative with respect to HR is just Fo. It's just like in multiplications. So this is what I have. And now there are a series of steps that I will go quickly because they are not difficult. If I distribute that, remember Fo, what is Fo? Fo, if my observed image, Fo is Fi convolved by HD, degradation, plus noise. Fi hat is Fo convolved by HR, and Fo is what I just said. So if you put all that together, you see that if you distribute, you have expectation of Fi Fo equal multiplication of Fi by Fo, and Fi hat is Fo convolved by HR. It's a bit of gymnastics, but you will do it your own. So you have Fo and HR here. And if you do it correctly, this is what you get. Expectation of the dot product and a convolution here, which is obviously not so funny. But this is, if you remember your courses of statistical signal processing, this is the intercorrelation, and this is the autocorrelation of 2 random signals. Expectation of a signal by itself is the autocorrelation of a signal. Expectation of a signal by another signal is the intercorrelation of 2 signals. You have to go back to your statistical signal processing courses, or you have to trust me. Intercorrelation and autocorrelation. So intercorrelation and autocorrelation here. And this is a convolution. We don't like that, so we move to the Fourier domain again. We will have the Fourier transform of the intercorrelation equals the product of the Fourier transform of the autocorrelation by the Fourier transform of the filter I'm looking for, HR. So again, trust me, I write it. This is what I had before. Fourier transform of that will be equal to the Fourier transform of that times the Fourier transform of that. So if I isolate HR, I get the Fourier transform of my restoration filter is the ratio between the Fourier transform of the intercorrelation by the Fourier transform of the autocorrelation. And they have name. This is the power spectrum of a signal, and this is the power interspectrum of a signal. These are known statistical quantities. And so now I have an expression for the ideal restoration filter that will minimize the difference between the 2. I just have to find how to calculate those 2 quantities. And again, I will not go into details. For those of you who don't know what I will say after, I just refer to basic statistical signal processing courses. You can find tutorials on Moodle, on Google if you want. But they are basic statistical signal processing. Those 2 quantities can be estimated knowing the spectrum of the image and the noise because of this. And this has the name Wiener. You probably have heard this name somewhere in one of the courses, Theorem de Wiener-Khinchin theorem. Some of you might have heard about that, not all of you. Just Google that and you will find what it is. But what it is this. The power spectrum, if you have a system with an input, an impulse response, and an output, a linear system, a signal goes through a system, so you have the input, the impulse response of the linear system, and an output. The power spectrum of the output is related to the power spectrum of the input by the square of the frequency response, which is logical. Huh? The output is the input convolved by the impulse response. So in the Fourier domain, the spectrum of the output is the spectrum of the input times the frequency response, classical linear. And in the power domain, to the square, the power of the output is the square of the frequency response times the power of the input, plus the noise. So that's logical. And the same applies for the interspectrum. And I will not describe it, trust me. The power spectrum, the interspectrum of the output is related to the power spectrum of the input by the complex conjugated of the frequency response. Trust that those two formulas are true. Then if you play with that, you get the final formula for the Wiener filter. So what it means, and I need another 3 minutes and I'll be done. It means that you can calculate the ideal restoration filter if you know the degradation filter, and if you can estimate the power spectrum of the noise and the power spectrum of your image. And this is where the intuition at the beginning comes back. Look at that expression. It might look a bit complicated to you, but it's very simple. And this is what I expect you to remember, how to interpret that formula. Let's take the simple case where the noise is 0. What is the best restoration filter if the noise is 0? Inverse filter, right? If the noise is 0, this term disappears. What do you get? Complex conjugated divided by the square of the module. If you remember your complex calculation courses, complex conjugated divided by the square of the module, this is 1 over the complex number. So you basically get, indeed, restoration filter is the inverse filter. Good. It works. And then, it's the inverse filter when the noise is 0. And so, it really behaves for each frequency as an inverse filter. For each frequency, it's an inverse filter if the noise at that frequency is 0. You really restore. But, if at that frequency that you are considering, the noise becomes significantly powerful with respect to the power of the image at that frequency, then it's not the inverse filter anymore. This term becomes bigger. You start to have a bigger term of the denominator. And so instead of being an inverse filter, for those frequencies where you have significant noise, this term becoming big, the value tends to 0. This becomes big, so the whole stuff becomes small. So at those frequencies where you have a high noise, the coefficient of the filter, the amplification factor, becomes very small. Instead of being the inverse, it becomes 0. It doesn't amplify, it puts the value to 0, it filters. So that's the Wiener filter. For each frequency, it estimates whether the power of the noise is significant with respect to the power of the image, whether it is a good idea or not to do an inverse filter, or on the other, or conversely to really filter out, put a 0 value, a small value. So basically, adaptively, depending on the content of the noise, depending on the content of the image, each frequency will be amplified by a value that ranges from the inverse filter if there is no noise, to 0 if there is an infinite noise. And in between, it finds the best trade-off to do a little bit of inverse filter or not. That's really the Wiener filter. Is it kind of clear what it does? At each frequency, it estimates whether or not it's a good idea to do the inverse filter, or whether you should rather put down the values of your image at that frequency. Yes?
But this worked equally well instead of the power spectrum of noise and the ideal image we had
The?
The original Fourier transform.
Yes, well, that was my next comment, how to estimate that. Actually, the power spectrum of the noise and the image you estimate by the square of the power spectrum, of the Fourier transform. So basically now, the last question that we have to answer, and there are just a couple of them, how do we estimate that? How do we estimate that? How do we estimate that? Now let's take them one by one. Now let me first illustrate what this is about. Again, my little drawings, and I will go quickly. My image. You will tell me, yes, but you don't know the image. Okay, I'll come back to that. Spectrum of my image. Kind of a low pass, not natural image. Affected by a white noise. Let's say it's a white noise. Just an assumption. Huh? This is the spectrum of my white noise. So my image that I receive is the image degraded by this low pass filter. Let's say this is the low pass filter that has been blurring my image, plus noise. What the Wiener filter will do is that for each frequency, that one, that one, that one, that one, that one, it will estimate this ratio between the power of the image and the power of the spectrum, of the noise. Let's take that frequency here. This is the axis of frequencies. Huh? Let's take that frequency here. For that frequency, obviously, I have a high power in the image, higher than the power of the noise, obviously. After degradation, I have more power in the image than in the noise. So obviously, for that frequency, it's probably a good idea to do the inverse filter. If the degradation filter was that one, around those frequencies, it's a good idea to have a shape like we have seen before, a restoration filter, the inverse of that. And for all those ranges of frequencies here, obviously the power of the image is higher than the power of the noise. So for all those frequencies here, it has a shape like the inverse filter. But at some point in frequency, somewhere here, the power of the image becomes equal to the power of the noise. So, warning. After that frequency, it's probably not a good idea to do the inverse filter because you will boost the noise and more than you will restore the image. So after a certain frequency, the Wiener filter automatically detects that and will filter the noise. Will filter the image, but mostly the noise because it's mostly the noise at those frequencies. So it behaves like an inverse filter when it can do a good job, and it behaves like a cutting filter, a low-pass filter, when it can do when it's a good idea to do the low-pass filter. And that's really the Wiener filter. And it works really increasingly well, impressively well. Look at this blurred and degraded image. After restoration, you get that. This is very crappy images, but you still get very nice results. This is blurred, and you can restore. The content is still there, but it's blurred. You undo it while controlling the noise. And the last thing that I have to tell you is how to estimate those values here. Well, basically, you have everything here. If you want to estimate the power spectrum of Fi, you just have to have the power spectrum of your observed image, know the degradation filter, estimate the noise, and you get that here. So you can get everything. Final, how do you get an estimate of the noise? How do you think you can get an estimate of the noise in an image? I give you an image. I give you that image. Can you estimate the noise? Where do you see the noise? Where do you see noise? Well, maybe you don't see much noise here. But in the Peppers picture that I showed before, there was noise. Where do you see the noise?
White line.
Well, that's not really the noise. The white line will tell you something else.
The ground.
Oh, yeah, the background.
No, the ground.
Yeah, here. Okay.
Yeah.
Yes, you take a region that is uniform, that is supposed to be uniform. Let's say the white region here, or the white line here. It's supposed to be uniformly white, but obviously it is not. So here you see the noise. So now take a patch here, remove the mean, remove the white, and the rest will be the noise. Take the Fourier transform, as you said, of that little patch to the square, and you have your estimate of the power spectrum of the noise. So you take a patch where you know that it should be uniform, and if it's not uniform, this is because of the noise. And finally, how can you estimate the HD, the degradation filter? Same question. How do you see that this image is blurred? How do you see that this image is blurred? Yeah. This should be a very sharp edge, and it's like a smooth edge. So basically what you see here is the result of the degradation. It should be a step function. It's a blurred. So this is really the result of the convolution of a step by your impulse response, by HD. So from that profile, it's easy to estimate HD. It's just the result of the convolution of a step. And if you know that if you take a step function and you differentiate it, you get an impulse. So if you get the response to a step and you differentiate it, you get the response to a pulse. And the response to a pulse is by definition the impulse response. So from the response to an edge, you really see the impulse response. To be precise, the integral of the response. So to make a long story short, now you have everything to calculate this. You know how to calculate HD, and if you didn't get it, just listen back to the video, you will understand. You know how to calculate the noise, and you know how to calculate that because it's here, and you can easily calculate all the other components. And that's it. I will stop here. Just one last word on the slide here. How do you calculate HD? You said by taking an edge, finding an edge. Yes, and that was actually done in a very nice experiment where a satellite had to be calibrated because the lenses were not totally straight. So the images had to be restored by a Wiener filter, so they had to estimate the impulse response of the telescope. And what they actually did was very simple. They went to a place in the desert where there were white sand, and they put a piece of tissue of 3 kilometers square. And what you see in the satellite was this. You see it. And you know that it's supposed to be white, black, white, white, blue, white. And when you see that, you really see the integral of the impulse response of your telescope. You see what is called the index response. You differentiate that and you get your impulse response of your telescope experimentally. You just have to go in a place where you can put a 3 kilometers square tissue. That's life. But that has been done. Huh? Those guys have been doing it. Funny, huh? Old tech. Okay, thank you very much for your attention. The recording will be available early next week. And we meet again here next week on Friday for the second lecture. Have a good day. Thank you.